you really never see nowadays on modern electric VTOL aircraft. But back in those days, it's pretty well all we had. Right through to basically the same design aircraft, a different version, different model of it, located right now in my labs in Nottingham. So the story goes back a fair way, and this is what led me into working at QUT in Brisbane, and then ultimately led me to working here in University of Nottingham, still roughly on the same kinds of projects. A little other background of some of the experience I had in Australia, which may be of interest, and I can recommend it to anyone. In hang gliding, people nowadays may be more familiar with paragliding, which is more of a parachute style of glider. But if you've never been hang gliding or paragliding, I can recommend it. You learn really a lot about aircraft and flying and the sky and things like that. So it's part of my background, one of the reasons why I'm interested in getting into the air. And from quite an early age, I was actually flying model airplanes, so radio-controlled aircraft. And typically those are, those hobby-scale model aircraft that you might be well familiar with, is radio control. Having done that from quite a young age and developing through, eventually when flight control systems, automatic flight control navigation systems started to become available for civilian use and research use, those skills transferred quite directly into the university. So this is one of the very early first UAV prototype aircraft we were flying in the university. And you can see actually the progression from the very basic hobby aircraft, which is very inexpensive, easy to get, easy to fly, but not always really useful as a UAV to operate and install the various systems that you have to operate to make a good UAV. So we started off basically converting it into a low wing aircraft. That way we had better access in the top hats to the systems on board. And then it evolved a little bit further into an aircraft that was very successfully flown for several years in undergraduate UAV research program at the university. And then we developed it a bit further using the same basic, very inexpensive hobby grade model aircraft kit, but just needing a bit more space inside for other systems, experimental payloads for navigation and geospatial work. And so it turned out to be the most convenient, best way to get more space in the aircraft was to actually double it up. And so using two of the original fuselages joined side by side, adding a little bit of wing root area, adding again, just some vertical and horizontal stability at the back. We ended up with a very useful UAV, very inexpensive, very easy to handle, very easy to operate. And in fact, I'm just putting this as an example that you can really start from small things, and in the research and development space, in the engineering space, it can lead to really interesting things. So this is a publication that we were able to provide for quite a prestigious journal using this small aircraft for geospatial work, and things developed from there. But the example is that you can do a lot with not much, particularly when you're starting off in, with limited funding in a small research environment. But it builds up, and you can get some really good outcomes in the future. Now, as part of that process of using those small UAVs, hobby grade engines, if anyone's ever used one of those, you'll know that they can be quite annoying things to operate in terms of starting the engines. Also in having onboard charging capability, you have to carry a lot of batteries and that kind of system. So back quite in the early days, the idea started to germinate that we could potentially have a hybrid electric power plant for, in this case, particularly for UAVs, that would have self-starting, so an onboard starter motor. And then you would have the problem of the extra mass and complexity, and you have to justify that to make a good system optimization. So perhaps the starter could actually do another job. It could be a generator. so electrical start and generator. This gives you a big advantage in terms of the overall mass of the aircraft. You can carry less battery. So we put that together and started to run it up in the wind tunnel to get good data out of it to see what the performance was. And then we realized that there's another advantage that can accrue is the efficiency of the engine itself. So this particular engine is very inefficient, actually. And one of the limiting factors is the propeller size that you have to use is relatively small because it's got a limited operating range on the engine. But with the addition of that electric motor, potentially you can run a larger propeller, which has got some higher efficiency potential. So in this case, I put on a much larger propeller, about 30% to 40% larger than that engine can handle on its own. But within the operating conditions of from static to dynamic flight, and using the starter generator as a booster to bring the engine up through the limitations of its torque potential in its cycle, I realised that can actually work, and it'll actually yield a positive advantage in efficiency, and therefore reduce fuel, and therefore, again, you can optimise the overall system. And then if you've got an electric motor on your propeller, then there's another advantage you can get. So I started to do some experiments here with the propeller operating as a wind turbine. And in this case, I just substituted a DC generator for simplicity. And you can see the dynamometer that I made for this project. So we can measure thrust, we can measure torque. In this case, it's measuring the drag. But in thrust orientation, we know the thrust, we know the fuel flow and the airspeed, and so we can derive the efficiency out of it. And it turns out we could get a big efficiency advantage. We had a big performance advantage, and so combining those things, it allowed to justify the extra complexity. And so this kind of fundamental research also leads to bigger and better things. And when I started doing this research, really about 20 years ago, it was unheard of, really. There had been some small studies, but really no one was taking it seriously at all. But as you'll see later, it's very serious business now indeed. So here's just some pictures of the later work we did. So we started off using those very small hobby-grade UAVs in a small research program in the university. And then we the university got some better grants, got some much better attention, and we ended up doing this big project called Smart Skies, which was for airspace management and utilisation. And we used the drones, we used the helicopter, and you can see the fixed wing machine there. Each one had quite sophisticated navigation and communication equipment on board, as well as the autopilots. And the idea was to come up with some algorithms and test them for automatic airspace management purposes, so that you could program your airspace management system, operate the aircraft automatically so that they would deconflict and optimize the navigation. So we had actually, in addition to the UAVs, we had a full-size Cessna 172, which was operating in the same airspace. We had a ground-based radar, we had a ground control station, and things were linked via satellite communications, Iridium, as well as cell phone networks in parallel, with some stations in the US and also in the UK in real time, managing the whole system. So the results there were very successful. And again, this UAV here, the fixed wing, had we were overloading it. We had a lot of systems to carry. We were running off grass airstrips, different conditions. It was poorly optimized for performance. The engine was just barely big enough, really, and the thrust was just barely enough to get off the ground sometimes. And that reinforced to me the need for hybrid propulsion to get that benefit of extra thrust boost for takeoff, reduced battery capacity requirements, and a general optimization, which we're still working on, and is now currently, this was 12 years ago. Nowadays, you're starting to really see this coming to the industry. So A little after that project finished up, had the opportunity personally to move to Hungary for a new job, change of scene, working outside of home country, which is a real eye-opener, very well worthwhile for people to do. And I got involved with the local flying club in the little city where I was living and working. And great experience. I'm sure if you've not had the opportunity to go flying any kind of aircraft, but in this case a motor glider, it's really lovely when you can take off, switch the engine off, and still climb, keep flying. Bit of aerobatics, and interestingly, from my perspective in Australia, we rarely would ever have the opportunity, but you find this in different cultures and different places, the way they operate. So one particular occasion, we were flying at the local aerodrome in Hungary that I was living nearby, and I was flying the motor glider at the time off grass runway here, and parallel adjacent to a bitumen runway that was handling regular GA traffic. Next to that was a winching operation where they were winching up sailplanes. There were model aircraft, about half a dozen model aircraft flying at the edge of the airfield here. And meanwhile, there were parachuting operations, which were coming in, and there was also a paraglider winch in operation. And all this was happening at the same time, and everything was being managed well by the people who were there, experienced in managing that. But to me, it was really a surprise, because that's something I don't think we would ever see in Australia, for example. But that's why you have to travel and learn about other things. So this is just a little brief background. The reason I was in Hungary was to work on the engineering of laser equipment for a research lab. And so it's also a very good way to expand your skill set. If you're a mechanical engineer or aerospace engineer, don't be too constrained. You can learn a lot if you get out there and do some other stuff. From there, I've moved to Nottingham in the UK, and that was about a little over 4 years ago. The job happened to come up. They were after a research engineer or a research fellow in hybrid electric propulsion for aircraft. Clearly, I'd had some good experience in that, and I saw this opportunity come up, and I wasn't far away. It wasn't like I had to move all the way from Australia. I was just crossing Europe. So I came over here and started working at this university, which is it's got two main campuses. One mostly for undergraduate students and some research, and then another one that's mostly geared towards research. So our buildings here, we've got quite a lot of area here for laboratory space and office and research space. And so up until February this year, this is where we're working every day. And now you can see we've been working from home for the last 4 or 5 months. Now, this is where it's at. So I wanted to just include a sample. I mean, some people may have seen these, but for those who haven't, these are all current leading edge developments of hybrid electric aircraft, spanning from relatively small commuter, sub-regional, VTOL, eVTOL, electric vertical takeoff and landing, air taxi, right through to regional airliner, and right through to relatively heavy, longer haul type airliners. Typically, this one would be turbo electric, so some kind of gas turbine operating electric generators, operating electric fans. A parallel hybrid electric setup, so this is where you have your conventional turbo shaft engine changed out for a hybrid version. In this case, it's a parallel hybrid, so there's an electric motor on the same shaft as the output of the gas turbine. That's actually exactly the same arrangement that I was using in the small-scale UAV experimental power plant. This is a series hybrid gas turbine turbo electric aircraft. By the way, this BAE 146 aircraft was being developed as a full demonstrator. University of Nottingham is doing work on that project in the electrical machines. Recently, partly due to COVID, the project has been scaled down, they're still developing the whole drivetrain for the aircraft, but they decided not to actually build the demonstrator complete. And I just read in the news today that this project also, I think it's still continuing, but they've slowed it down. But the impetus for it remains. There's very, very significant emissions control regulations that are oncoming to the aviation industry, and hybrid propulsion is seen as one of the ways to improve the emissions performance and reduce emissions. And it can work actually. It's a bit more viable at the moment for some categories of aircraft than pure electric. Pure electric does work on smaller scale aircraft at the moment with some limitations. We'll talk about that in a moment. But these hybrid versions, and it can be hybrid internal combustion, it can be hybrid with fuel cell technology, but the idea is that you're not constrained to the energy density limitations of batteries as we have them at the moment, but you can still yield some very good efficiency advantages, and you can change the nature of where your energy is coming from, the whole supply and process of the energy. So those are worth looking up. I'll mention this one as well. There's a French development that's based on Cessna 337, which you might realise it's a push-pull aircraft originally. Now it's been developed with two pure electric propulsors on the pods here, with a rear engine. The engine drives electric generators and also drives a propeller. So it's actually a full hybrid propulsion unit, and it's currently flying as a prototype, and then the full new version is actually in development. And you can see here a electric VTOL. It's a Rolls-Royce electric VTOL concept, German concept for again parallel series hybrid. One of the advantages that's seen, and I'll talk a little later, is being able to spread the propulsion around. So you can have a core generator set, but you can actually have spread propulsion, and you can get some propulsion efficiency advantages out of that. So right now, I just want to go to one of my main projects, which I've been working on for the last 2 years as a core demonstrator project within the university. That's AeSN. Now, there are some videos here. I'm not going to play them on this presentation online, because I know that sometimes when you try to play a video over the net here, you can have interruptions and problems. But if you look up AeSN videos online, you'll no doubt find them, and you'll see some exciting stuff. There's a link there to aersn.com, the website, and later when you get the slides, you can look up that particular link. But so this is a demonstrator project. The university wanted to develop a research demonstrator for pure electric propulsion. One of our core strengths at Nottingham is in electric machines and power electronics. And we've been doing that for a long time in different industries, and lately much more into aerospace and transport. So we had to think of a good scale aircraft to get a hold of to modify and change out to electric propulsion. We've already been doing motorcycles for a while, so another demonstrator we've had is a pure electric motorcycle race machine, which has been very successful on the electric motorcycle racing scene. A lot of Nottingham developed propulsion technology in there, including the motor and power electronics, of course, and then the whole system integration. So when we came to look at what kind of aircraft we could do, and we came across AeSN, which is a very small single-seat racing aircraft designed for flying at low level around a set of pylons, about a 2-kilometre course. They're racing about 4 to 8 aircraft at a time. But the aircraft is quite small, and we realised that a lot of the experience we had on the motorcycle is roughly the same kind of size, power and weight as is required for this size aircraft. So we set up a project to retrofit an electric propulsion system. This aircraft originally is fitted with a Continental O200 engine. It's a standard engine for the class. So we just have removed that, and we're looking at what kind of electric propulsion system to put in. So the project is divided into the electrical system design, mechanical system design, procurement of big costs. It's always a big problem in any project is procuring all materials, battery cells, motor, power electronics, the mechanical design, and then the integration design, and then of course airworthiness. So the rules of the class are based on an original class, as I said, with the O200. The new class is scaled so that basically the airframe is the same. The power limit is set currently at 150 kilowatts. The original class and the original engine was completely maxing at 150. Typically that'd be about 100, maybe a little lower than 100 kilowatts. But the AeSN organisation wanted to make sure that we were at the cutting edge and we were relevant and it was exciting. So they've gone for a 150 kilowatt power plant in what is a very small aircraft. So you can imagine the performance potential of these things. Now, the reason why this is viable for electric at the moment, whereas a lot of electric aircraft are not viable because of the limitations of battery energy density, but the races are about 5 minutes. And so for this size aircraft, we know that with the amount of mass that we can put on board, we can limit it at 150 kilowatts, and we should be able to get around a race of about 5 minutes if everything is optimized. But this is a maximum power, and you don't have to go to the maximum. There are other ways to go fast. There are other ways to minimize the course time, and so that's what makes it a really good optimization competition. So it's a technical competition as well as a flying competition. Very basic rules. So we're developing our initial demonstrator with one of these selections of motors that are actually available. So at the moment, there are mostly motors that have been designed for automotive, but you're increasingly seeing specialist aircraft electric motor design on the market. This here is a YASA motor. This is the one we selected. It's a UK designed and developed motor. It's actually an automotive motor, but we find it should be quite useful for the aerospace, particularly in our application. MRAX produces a big range of electric motors that are very well used at the moment in aerospace research and development and even commercial projects. Safran has developed a specific, highly optimized aerospace motor. Very, very good one to look at. Still quite expensive, but very, very high performance. And recently, Rolls-Royce by Siemens developed, and Rolls-Royce has bought that armoured company in very, very high performance aircraft grade electric motors. And then there's a few others that are around. And one of the things about AeSN is that it's a competition where you can bring in whatever technology you can integrate. It doesn't have to be specifically one thing or another. You can select from a variety of options to try to get a system that works to the requirements. So what we've done is we've taken this Casset 3 aircraft, which is an old design, very, very popular in the sport. They're typically built by home builders or in small production runs, not a factory-built aircraft. So quite easy for us to get a hold of, quite economical to get a hold of. So we pulled out the original engine, and then we had a range of equipment to select from to replace as an electrical propulsion system. So I'll just go around what that is. You have to have a pilot interface, so you've got to control that just as you need an engine control, something to control the thrust output. You need to have instrumentation to say what's going on. It's slightly different from the conventional, but you basically have to know how much power you're applying, temperatures and any relevant pressures, particularly temperatures, voltage levels of your battery pack, and that kind of information. So we've selected this as a fully programmable pilot display here. A computer to manage the whole system. Obviously the electric motor, this is the main motor here, the YASA, an inverter. So this is a three-phase permanent magnet motor. It needs to have an inverter to take the DC from the battery system. The battery system itself made up of multiple cells to get the voltage, to get the capacity. A management system for the batteries, so battery management system, which can monitor and control the battery, monitor the cell voltages and temperatures. We have to have a cooling system, unfortunately, for this particular motor and this particular inverter. They both run liquid cooling, and they're two separate independent circuits. So we have heat exchangers and pumps. And then we have a charging system. So that's the other point to the project, is to have a charging system. It's charged on the ground. It's possible to have batteries that are demounted and changed out, but in this particular case, we'll be doing ground charging. So just a little more detail in the battery system that we're developing. It's based, as I said, on our motorcycle work. We're using pouch-type cells, lithium polymer pouch-type cells. There's a couple of different configurations to get the voltage. This is actually an old schema. We've changed this since this was drawn up. You can see the voltage there, 350. Well, that's actually relatively low voltage these days for this kind of equipment. We've gone to 800 volts now, which gives you a better efficiency overall for this particular inverter and motor we're running. Less losses, but you obviously have to be very careful with handling these. Even anything over 80, 100 volts is something you have to be very careful with. So that's part of the problem. Putting these up in series configuration. We're doing circuit boards. I'll show you a little detail of that. Circuit board to manage each of the cells have to be put together with bus bars. They have to have their own temperature sensors, voltage sensors. So that comes onto a custom designed circuit board here. And then fitting it into the aircraft, we're wanting to do this quite simply in the first phase of the project. We'll have another phase where we optimize everything, but in the first phase, we wanted to keep it simple, straightforward. So we just changed out the original fuel tank area and the original cylinder head area of the where the engine was mounted for battery packs. And we've actually included the battery packs in a modular arrangement with a fireproof enclosure. You probably realise that one of the critical hazards is fire, well, in general on aircraft, but also when you're running a battery pack. Here's the motorcycle arrangement. You can see most of the motorcycle, in this case, is made up of battery packs, and they're not actually insulated. Something goes wrong on the bike, you can pull up and get off. In the aircraft, we need a little more control over the situation, allow time for the pilot if there is a problem to come and land. Each of the battery modules is made up of subpacks, bricks, which are laid up of individual pouch cells, and then included with bus bars, and then they get connected to the other bricks. And you can see here the voltage and temperature type sensors that get output to the control unit. Just a view here of our battery containers and one of the cells. So there's several hundred. I think there's about can't remember now exactly 300 or 400 of these individual cells, which are then stacked up and then put into these composite material. It's quite an advanced composite that won't burn up to about 800 degrees C. So we'll be installing these into the aircraft. And this is just a view of how these cells come from the factory. We've got 1,000 of them there, which is good enough for at least two sets of batteries for our aircraft. So in terms of installing this motor into the aircraft and retrofitting it to where the original engine was, as I said, we didn't want to make too many modifications, so we wanted to keep it simple to start with. So the red colour here is the original truss that mounts up the original engine, and we've kept that. And then we've had to make an adapter system to this AeSN motor. Now the AeSN is not actually designed to do this. It's designed to be installed in a car. You can only put torque onto the rotor of this motor. You can't put any kind of bending. It hasn't got internal bearing set for that. So we had to arrange an external bearing set in a spindle shaft mount, which was also then transferring the propeller loads through the casing of the motor very carefully to spread the loads into the truss for the engine mount. So it's not optimal. It's heavier than it needs to be potentially, but it should be safe, reliable, and also quite variable for future installations. We can use the same spindle shaft here for different motors and different configurations. And you can see we did some FEA analysis just to ensure that there were no problems with the overall stressing of the system. And this was done in accordance with the limitations for Part 23. But the aircraft itself, it doesn't need to be certified. It's flown under a different permit to fly arrangement, but we wanted to use a particular standard, and the Part 23 seemed the most applicable. So this was back earlier this year, just getting some of the parts organised, manufactured, and then taken to an aerospace maintenance facility. The university is not an aerospace organisation. We've got skills in technology, but we wanted to find a specialist who could put the aircraft together properly. So East Midlands Helicopters is a local company that's very friendly and has all the right skills. So one of the advantages of this scale of aircraft in doing this kind of work is we could actually fit it in this van. So once the engine and the wing were demounted, we could actually fit the whole aircraft inside a standard van and get it to the site. So a little later, in that facility, we had all of this machinery which was made up and installed. So here you can see that what was designed has been manufactured, put together, installed in the aircraft. Fortunately, everything fitted. That was helped by some of the CAD work we did. We actually were able to scan the aircraft with a laser scanner and then put it into CAD, because the original aircraft was designed well, in the 50s, well before anything like modern CAD systems were available. So there were no CAD pictures or drawings of any type. So in laying it out to make everything was going to make sure everything was going to fit, we used a scanned model and then put it into CAD, and then we were able to fit the components virtually. And then luckily, once we actually had the real objects, we found that they actually did fit pretty close anyway. There were a few items where we knew we were going to compromise and have to make some extra cutouts, but it's not a big compromise. And so that's actually where it's at the moment. We still have to finish the battery packs, and we have to install the cooling system and other systems, but we've been held up with the COVID issues lately. In the meantime, as a parallel project, there was an opportunity to use a different system that had already been developed for another application and put it on board an aircraft for display at Dubai last year. So I had the right connections who were doing this work already, and they had an airframe, and another company had the propulsion system, and this particular one is different. It's a specialized unit for other applications. You can see a contra-rotating electric propulsion system on board here. Now, this has got some, this shows off some of the advantages of electric motors. There's lots of pros and cons, advantages and disadvantages, but one of the advantages is the way you can lay them out. And in this case, you can see two motors back to back. They're actually the same type of motor that we're using for our single installation, but this one has been developed specifically for contra-rotating, coaxial contra-rotating. So you can actually run the shaft of one through the rotor of the other. And it's very convenient, compact, easy way to do it. The traditional method with combustion engines and crankshafts and everything is much more complicated, much heavier. And you can see, the value that we got out of doing that project in displaying. It's only a static display here. We weren't flying the aircraft, but we got a lot of good value and outcomes out of that sub-project. So I guess this is kind of advertising for the companies that I was able to get involved. One of the things about doing these projects is that you do get really good networks. So if we weren't doing our university project on this with AeSN, there's no way I would have met these other companies. I couldn't have brought them together. we couldn't have had that result. You can see the power plant here, actually, that's on board the airplane, and it was tested on board a rig, full rig, dynamometry on board an electric car. So you can actually power the car using the thrust from the motors, and you can obviously take a lot of data and get a lot of really interesting results out of that. Just another advertising picture to. I do these kinds of presentations, and we're always looking for sponsors. So yeah, that's it right here, and I can take more questions about that later. But moving on to a separate project, another one. These are electric aircraft, pure electric aircraft, some of which are available today, some of which were available commercially very soon. So this is a two-seat side-by-side pure electric propulsion trainer being produced by Aerospace in the US. It's going for Part 23 certification right now. I think they're quite advanced in that. It's probably going to be certified either this year or sometime next year. This was a demonstrator done by Airbus and as a demonstrator project, very successfully done. Twin engine, electric engine. I should call it a Moto. This was a Siemens demonstrator that's pure electric, extra 300 aerobatic airplane, holds several records at the moment. Time to climb. There's various advantages you can get. The main disadvantage of the electric propulsion system is the energy available. It's much, much less than you can get out of fuel and a thermal engine. But if your mission only requires short endurance, then some of the performance advantages are really good. This is a pipistrel Alpha Electro. I think it's just been certified. It's been on the commercial market for several years. Pure electric. It's the same airframe as what they sell with a petrol engine, but it has some unique advantages. It is quieter, it is smoother, it's much cheaper to operate, but the disadvantage is that your endurance is limited to around about 1 hour, whereas if you were running the petrol engine, you'd have 3 to 4 hours endurance and then corresponding range in that aircraft. So as a buyer, in the market, you might wonder what you should buy. It depends on what your intended mission is, obviously, but you might not know what that is. You might need to have something that you in the future you might be thinking you do want to have that range, and so your decision to buy it or not is affected by that. So as a researcher, as a research problem, that was a good one to look at. If you're flying an electric aircraft, you're just going to get about a quarter or a third of the range and endurance. So what can you do about that? Another problem with flying private aircraft or flying small aircraft, if you actually want to go somewhere and do something with that aircraft, is what happens when you get to your destination. Do you have transport when you get to where you're going? You might find you're landing in an airstrip like this in somewhere regional, somewhere outback. You might find the only option for a taxi, disappeared years ago, and then same with the bus. And so you're trapped. And so would you then choose to drive rather than fly? Unfortunately, that's what happens most of the time. People don't buy the aircraft because they realize that there's no, they're not going to be able to use it, even if it had the range. So what can we do about that? Well, the idea here is to have your pure electric aircraft, such as the ones I was showing you earlier, with a range extender added to it as an optional accessory. The problem is there's a big compromise there of payload, drag, and other issues, cost and utility. So we decided to have a modular system that was easy to put on the aircraft, easy to remove from the aircraft. There's quite a bit of mass in this thing if it's going to have enough energy to supply for this kind of aircraft, around about 20 to 40 kilowatts, so an engine, a fuel tank, a generator. So we thought it better have wheels, and you could roll it around the tarmac and then jack it up to the aircraft. So once we realized that having wheels, electric generator, fuel tank, etc., was going to be there anyway, potentially suspension to jack it up, it seemed to make sense that it should be multifunctional. So I had the idea of creating a scooter. So this is the same unit as you see on that aircraft, but it's unfolded into a scooter that you can actually ride to to the airfield. It has the features of wheels, suspension, so you can jack it up and jack it down. You can close the windscreen, and you've got this whole other use as a scooter. And then you can fold it down and put it on the aircraft for that duty, that range extender duty, as and when you need it. And obviously, you can also then go to your meeting after you've landed at the airfield where you need to go. So just a use case cartoon here. You know, you can see you riding it to the airfield. You get to the airfield, you close it down, you jack it up under the aircraft, pin it on, put the plugs in. And that provides you with that extra endurance, because your energy value of the fuel you're burning, even though it's inefficiently being combusted, got to go through a generator, go through power electronics. Even after all of those stages, it's still about 3 times better than the quantity of battery you could carry. And then you've got this advantage of having landed and being able to get where you're going. And then, of course, there are other uses for this kind of mobile power generating system that's, you know, quite high powered. So you could, you know, potentially use it as on-site power or camping. So it's been quite an interesting project. We're actually developing a demonstrator for that, just as a basic technology demonstrator, using a very simple, cheap, pure electric scooter of about the right size. And then we looked at what kind of engine generator setup we could get for that, using commercial components, and how it would fit together and demonstrate the concept without having to go through the whole product development cycle. So we've used a small rotary engine. In this case, it doesn't need to be, but the rotary's got some advantages and some disadvantages. One of the advantages is it's compact, and it's got a pretty good power to weight ratio. But once it's all installed with the accessories, the ancillaries, the cooling system, the lubrication system, the exhaust system, etc., it ends up being, you know, a bit of a size and mass. It's contained though, and you can see it here in a laboratory container that we can test it and get the electrical and the performance properties out of it. So we're running it here in the lab. It's designed to output 20 kilowatts at around 100 volts, and it does so. We ran it through a pure resistive load bank just to check the system. It's still under development. There's a few teething issues, but we are then planning to install it into that small scooter, integrate it up, and then modify the scooter to fold and close down. And then at some point in the future, we should be able to flight test that to complete that project. And then there's potential commercial applications. I still get calls, and there's still, you know, potential for commercializing that project. But obviously, people take a real interest in that multimodal aspect, what you can do with it. Even if you're not using it for aviation, just being able to have a hybrid electric scooter that you can run pure electric, put some battery on board, only start the engine when you need it, have zero emissions while you're in an urban environment, and then for longer range on the highway, you could start the engine and get full range out of it. So that's been quite an interesting project and a good one to be involved with. Other things that have come up. So I've been doing this basic project for some years. I started actually in Australia 8 years ago to develop a Part 23 type aircraft of similar size and capability of a Cessna Caravan, but with a few unique features. Full clean sheet composite design, same kind of size and weight, same kind of power plant as a Cessna Caravan, but with some really interesting features in terms of the overall size of the fuselage, what you can fit into it, and then some of the efficiency that you can get using modern composites in the design as compared to when the Caravan and others like it were designed and you had lots of limitations. But in that process, I then moving here and actually having to write papers for hybrid electric, I decided to see what that aircraft would look like if we hybridized it. And the other thing about the aircraft I should mention is that it was designed with skydiving as one of the main roles. Industrial partner in Australia is a very successful skydiving operator, international champion, and he's got this design, which he asked me to help with, to get the world's best skydiving aircraft. It is actually a significant market. And what's more, if you've got a very good skydiving aircraft, then it's very good for other operations. Looking, technically in the academic sphere about what it will look like, what's the performance likely to be, can we get some advantages if we put a hybrid electric system or even a pure electric system? Is it possible to have a 4-ton skydiving aircraft pure electric? So you can look up this paper, you can easily link for that, where I did some basic studies as to looking at the range of hybridization. So you can have a degree of hybridization from virtually no electric to full electric, and you want to find out what the pros and cons are, what the advantages and disadvantages are. It turned out, and I did this about 3 years ago, it turned out we could actually operate this aircraft as a skydiving aircraft with pure electric. We would need about 800 kilograms to 1 ton of battery, but it would still have enough payload for the mission. And if you think about the skydiving mission, you put a load on, might be 10 skydivers, might be more, and you go upstairs, come down and land, and then you want to do that cycle again. So it's basically full power all the way up, and then getting down is also really, getting down quickly is a very big part of the problem. It's a limitation in all the cases with a thermal engine, particularly piston engines. You have to regulate your descent so that you don't get shock cooling or other negative aspects. Whereas if you go to electric and hybrid electric, you can actually regulate that much better. The electric motors are much less sensitive to changes in altitude, changes in temperature. Electric motors are much better at high altitude. Even against the turbine, but particularly against the piston engine, having the density change and the performance change. So climb rates, you can maintain the climb rate much better if you've got electric propulsion on board. So in this case, you can see there's still a gas turbine engine in the front. It could be smaller. You can downscale it depending on how much battery you're carrying, and you can vary that. And then you can have pure electric motors on the wings in this case. And the other thing that happens is once you do that, it's actually very easy comparatively to install electric motors compared to installing gas engines. Much easier to run, much less maintenance, much less vibration, much less system control problems. But in this case, going from single propeller, which is limited in its diameter, limited in its area for other reasons, suddenly you've got 3 times the disk area. And you've reduced the disk loading therefore by 3 times, and you can actually really play with your performance, climb rates and efficiency simply by having distributed propulsion. And you'll see in many other aspects of other types of aircraft, putting more and more fans or propellers on the wing or in other places in the aircraft, you can really optimize and customize where you're getting your thrust and how you're developing the thrust. So this paper was quite successful. I think the aircraft design itself, it's ongoing. The developer is still looking for commercial partners and applications. If you know any and you get involved, then by all means let me know. Here's some other pictures of the way we're putting this aircraft together. You can see some of the particular features, plug-in wings and very large loading aperture and volumetric capacity on the fuselage. So again, back to skydiving. We're not in a position to do a clean sheet design, clean sheet Part 23, 4-ton aircraft. You can imagine the costs, the investment required for that. So with other partners, both in the UK and Australia, we started to look at what we might do with a smaller aircraft. And one of the smaller aircraft that's very often used in skydiving for small operations is a Cessna 182, so a 4-seat aircraft, and they can carry 4 skydivers on average to reasonable altitude. But it's an old design. The piston engines are worked very hard, and there's other drawbacks with using these aircraft. So maybe it's a good candidate for electrification. And then there's a couple of configurations that come up immediately. You might, as in some of those other examples, you might put the motors on the wing and spread them out, put a battery pack in the nose, do it that way. And I actually think that's a really good option. And I'd certainly want to look at that in depth in the future, but it's obviously going to be more expensive and more difficult than simply changing out the engine for a motor. But one of the things I found in the research was not only can we change out the original power plant to get the same power, we could actually really increase the power and then get an overall energy advantage, climb quicker, climb for less time, and maybe some advantages in the climb in terms of aerodynamic efficiency. And so if you were to put a single power plant on board and really increase the power, you'd start to get big problems with stability, structures, and other issues. So going back to the contra rotating, you can basically eliminate the torque problem. You can get a redundancy feature, and we can fit that into the nose of the aircraft. And in fact, in this particular study, I looked at how we would go if we put 300 kilowatts in this 182. The 182 standard power is about 235 horsepower rated piston engine. Some of them are actually, you can get an STC to put on, I think, 280 or maybe 300 horsepower, but no one at the moment that I know of in the world's put 300 kilowatts on board. But we think it is feasible using electric. And if you go electric, you then get some really good advantages in climb rate. The thing will climb at probably well over 2,000 feet per minute, maybe 3,000, whereas the piston engine unit, once you start to climb, really degrades in climb rate, whereas the electric machine won't really do that. So that's a project that's ongoing. We do have a company set up, and we are looking at doing that retrofit of that aircraft. And it would, I guess, I'm talking to an audience from potentially high altitude places, and so it's something to look at. Now I'm coming up for about an hour, and I've still got a few little things to talk about here, but I think the time's looking good. So I'll just spend a moment talking about other future concepts, where this kind of thinking leads to. Some concepts that I've come up with internally for the university, just to promote some conversation and also to represent some of the ideas that are now current in the highest level aerospace research areas. So you take a conventional fuselage design, might be 20, might be 40 seat, sub-regional, regional airliner. The key things here to look at is known as boundary layer ingestion, BLI. It's a feature you'll see on a lot of concepts now. The idea is to put the propulsor at the back here and draw in the boundary layer air that's been disturbed and lost flow across the fuselage separation. But to bring it back and get a laminar flow on the fuselage, you can really reduce the drag that way. There are some problems with ingesting a distorted flow field, but it's being done and ironed out, and you can get an overall efficiency advantage. The box wing concept, or really it's a canard type concept, but with a highly loaded, with a equally loaded front rear wing. There are some advantages there. There've been a few designs played with. I wanted to just represent it and as a talking point, but it's the sort of thing we could see coming in the future. It does lend itself to some of the features of the hybrid and electric scheme. This is a more conventional, but still a little, you can see obviously it's less conventional than what we normally have at the moment. Putting a high aspect ratio wing, very high aspect ratio, reducing the flight speed, really cutting the drag down, improving the efficiency of the aircraft, potentially improving range, or just really reducing the fuel flow by flying a little slower and much higher efficiency, much better L over D. You see here on this example is a boundary layer ingester system, but with a small disc, such as we have in a boundary layer ingester, you have a big disadvantage in the efficiency and the magnitude of thrust that you can develop at low speeds. So what if you were to put large diameter propulsors on it to do your takeoff and your initial climb? It's much quieter, it's more efficient. You get a much shorter takeoff run, much steeper climb out, much quieter at higher efficiency. But for cruise, You don't want that. You want to go fast. Have a disc loading tends to be better for higher speeds. So then you can simply feather these propellers. And if they're running off an electric motor, it's just no problem at all to turn that motor off, turn it on again. You can have your gas turbine either running parallel hybrid, so a generator and a motor set up in the fuselage. You could have small gas turbines arranged on the wing, running in a series hybrid configuration, a pure series configuration. There's just really a lot of options once you start to go down the hybrid electric route. Just in this particular case, you can count the number of options there are in terms of number of engines, where they're placed, how they're driving the propulsors, and so on. So the design space is really opened up, and it's obviously very complicated to try to optimize something out of that, but it's there to do. Now we're coming to my personal favourite project I came up with over the years, basically from the hang gliding experience, and not probably many people, some I'm sure in the audience, but not maybe many, and as many as which ought to be, have had the experience of open air flying, whether that's in a hang glider, a paraglider, or an open top aircraft, no canopy. So I wanted to have an open top glider. But the other thing is I didn't want to have one that's all restricted, 2 people at maximum in a very tight environment. So I wanted to have a multi-passenger glider, a motor glider. Once you go to multi-passenger commercial operations, having the engine on board to do the takeoff and the airspace management, airspace control is important. So a hybrid makes sense. You can run gas turbine engines to do everything you need to do, and then you can turn them off. And there's nothing better than turning the engine off when you're flying an aircraft, if it's equipped for that. Suddenly everything gets much quieter, much more comfortable, low vibration, and you can start to soar, and you can thermal and climb in clouds. So the idea was for this 6-passenger turbo electric motor glider for tourism, recreation, and it just happens to fit really well with the hybrid concept. So you can see here another illustration of that. You could be sitting with your friends, enjoying the scenery, having coffee. In the back, there would be a coffee machine, there would be a toilet, and facilities. You may or may not need the canopy closed for getting up and walking around. Okay, there's some problems that can be overcome. And if you're in a very cold environment, well, just put the canopy on and have the comfort, have a lounge, have some music playing, enjoy the scenery. So with that, I think I've covered everything. There's some really hard, proper kind of scientific stuff there. There's a little bit of stuff that's more exploratory and where we can go. We want to encourage innovation. So I'd be very happy to take some questions. I haven't been keeping up and reading the chat, but I'll just start to have a look at some of those right now, and I'll just hand over to Sudip to handle questions.
Okay, thank you, Richard. Fascinating concepts there. I actually have quite a lot of questions, but I'll have to also go to the questions that's on the chat box. So the open canopy concept, I hope you'll also have like a sign somewhere that says seat belts are mandatory, because I can almost imagine how open is it? Like
okay, so the concept is to have it completely as open as possible. And as you see in the picture there, that's what I want. I want you to be able to see out and see the clouds and touch the clouds, because when you're flying a hang glider or a paraglider, that's actually what happens. Anywhere you look, you're seeing what's outside. You can touch the clouds. Sure, you're going to have a restraint system. It's going to be super important and super critical. But it's not that far outside of imagination. Very early aircraft in the 1910s, and obviously the original aircraft that were ever invented were open canopy. And it's something we've lost, and it's something I think that it'd be lovely to be able to bring back.
Yeah, I mean, that would be really nice. So these will be relatively low speed gliders, right?
Yeah, one of the things about flying gliders is you want low speed for a couple of reasons. Obviously, in this case, reducing the wind noise, because that's one of the problems is the wind, a lot of airflow, turbulence and noise. But also when you're thermaling, one of the joys is to get a thermal, and this is what I want more people to understand and realize is flying a glider, intercepting a thermal, so warm air rising somewhere, and turning and climbing with no engines. And you can climb right up to the clouds and even beyond and higher in some cases. But in order to get into that thermal, it's a limited diameter. Usually, it could be a football field size. It could be the bigger ones, maybe 300 meters or something. But so you've got to be able to turn, and your turn diameter is really limited by your airspeed, and so you need to have a low wind loading. You need to have the capability of flying quite slow, let's say about 40 knots, and that makes it viable.
Right. So a question about that range extender: is it a separate power plant, like a fuel-based or a battery-based power plant?
Yeah. So the range extender is a thermal power plant. That could be piston, it could be rotary, it could be gas turbine, it could be fuel cell. But the idea is that you're using the energy content of the fuel, which is something like 50 times better than the current best battery. And you're taking advantage of that. Now, you put the fuel through an engine, and the engine might be 20 at best, 30, maybe 40% efficient. And so you're losing a lot of that energy to waste in that way. But and then through the power electronics and everything. But at the end, you're still way better by a factor of 4 or maybe even 10 than the best equivalent battery system at the moment. That's not to say things won't change in the future, but at the moment, you just get being able to use liquid fuel. You don't have to use it all the time. That's the beauty of the system, is that it's modular. You can have your pure electric aircraft running emissions-free on low-cost energy. But when you need it, you fuel it up, and then you can fly for your range.
Right. Okay, so I have a couple of more questions, but before that, I'll go to the questions from other attendees. So I'll read them, word by word as they've been as they're in the chat box. So first question is from Biraz Kharka. He asks, new technology means new power, electronics, new controls, new cooling system. How can we make a reliable, robust propulsion which replace the conventional ones? How are manufacturers proving this the right one? Meaning, like, how are manufacturing proving the reliability of subsystems?
Okay, yeah, that's really to the core of a lot of the issues. You're taking new systems that are new to aircraft. Typically, they haven't been designed for this right from scratch. We're starting to now, but in terms of certification, reliability, dependability, it has to be carefully done, and it's a difficult process. So I can speak to a few of these items, which we actually did research on in Nottingham in terms of power electronics, the particular types of semiconductor, being able to put them into test cells to simulate cycles, simulate altitude and thermal cycles. It's not my specialty, but I'm working with the people who are doing this. So right from the fundamental research in semiconductors through to how do you arrange these things, how do you handle the thermal problems. Just because you're running an electric motor doesn't mean to say you don't have to reject heat. There's heat loads involved. In some cases, that's actually trickier than a conventional gas turbine, which practically does it automatically. You can cool the oil, but a lot of that heat's coming out in the jet. So all of these things are being looked at. It's not new, actually. The propulsion side is relatively new, but the more electric aircraft side, where a lot of the systems, which traditionally were hydraulic or pneumatic, have definitely over the past 10 and more years gone electric. So you've got examples in the 787, in the A350, where a lot of the systems have been developed into much more powerful electrical grids. And so I can't speak in too much depth personally on these, but the issues are real, and the research is ongoing, and the implementation is actually happening in the field. So it's actually another area where It actually opens the space to new people to come in, different industries that have traditionally not been in aerospace, new things for aerospace to do. And yeah, so the problems are there to be solved, and they're being solved.
Yeah. So, I mean, while we have this range extender concept on the screen already, I'll come to another question from Sunil Dal about it. I think it's a fascinating concept, and I think it takes a lot of time to sort of unravel all the complexities and the exciting things behind it. I kind of feel like, given all the talk about air taxis nowadays, this kind of particularly touches on that pretty well. So a question from Sunil Dal about this is that, so a range extender is an electric system with an optional liquid fuel system attachment. Is that the case?
Sorry, can you just repeat that? I had to quickly make a message.
That's all right. So a range extender is an electric system with an optional liquid fuel system attachment. Is that?
Yeah, that's right. So, so the aircraft, the concept is that you have a completely electric aircraft, and only very, very minimal modifications required for fastening and for integrating the external power package. So you can fly the aircraft without this package on as pure electric. Then within the range extender, that is where you have your fuel, you have your electric generator, and you have your thermal thermal engine to run the generator. And so that's all self-contained. So there's obviously going to be some battery on board as well. And you can vary the amount of battery, and then you can vary the amount of fuel. So if you wanted to run the scooter as a hybrid scooter on the road, you could potentially change out that battery submodule for more fuel, or vice versa, so that you can vary the range that you've got, either pure electric or by fuel. So it's a hybrid scooter in effect.
So any chance this might itself be the primary propulsion system in some cases?
Well, yes. If you were to modify the unit again and put some propulsion system on board the range extender, because at some point you've got to run a fan, or a propeller somewhere. So where you have that, is variable, I suppose, but that would be I guess a departure from the concept.
Right. Okay. Okay. So another question is from Saksham Shrestha. Is it effective to operate hybrid electric aircrafts for medium and long haul flights? If so, how will it really play a role to reduce the CO2 emission constructed by the technology roadmap of IATA?
Yeah, so I think if I understand the question, and it's another very good one, the problem we have at the moment is that kerosene is a great fuel, and gas turbine engines are great machines, particularly for long haul, heavy aircraft. The efficiency of the turbo fan for those applications when they're in their operating point, if they're being operated according to the best strategy here, is something like 50% thermal efficiency after you go through the engine and after you go through the fan. So, and the energy availability within the kerosene is huge compared to anything else we've really got. Considering especially the way we can handle the fluid, so the handleability of it and the safety and everything that we've developed. Hydrogen is a contender, but storage, handling, and the sourcing of hydrogen is problematic, but it can be and is being looked at. Now, there are some potential ways to make electric propulsion work on long-haul heavy stuff. Obviously, it's been investigated quite thoroughly. The problem is in the energy storage. If you go to hybrid, there are ways of improving the efficiency in order to use the electric machines to drive the fans as compared to the pure gas turbine, but it's very difficult. When you're coming from a very, very highly developed, high efficiency base, as you add any system complexity and add efficiency links in the chain, you've got to have a very big payoff on some other attribute to allow for that. So the first examples that are going to make sense are the shorter haul, smaller aircraft, where you can do it with more battery on board, and not suffer the same kind of problems. But within the gas turbine, there is still scope, and one of the areas of development is to incorporate machines, electrical machines, within the cycle of the turbine. So you have 2 and 3 spool gas turbine gas generator cores, and there are trade-offs within there still in terms of the cycle between the stages, things like bleed air controls, anti-surge, and you can put an electric machine that's a generator and a motor between shafts or on shafts, and transfer energy between them. And there are ways of developing advantages like that. There's other ones where you can do electric taxi on the ground. So in certain cases, a lot of fuel is wasted on the ground taxiing. There's been some developments of e-taxi, like electric taxi wheels. At the moment, what I'd say in general is that the bigger and the longer range aircraft you're considering, the less easy it is to make it work in an electric or hybrid scheme. But there is a compulsion towards trying to do something to reduce the emissions, and incorporating electric systems is currently the best approach that we can see. There's some other approaches using sustainable fuels and so on. And at the moment, it's a juggling match, and different companies, different research organisations are going different ways, and you've basically got to do that. You've got to try to shake it down, do the research, figure out what the real viable ways forward are.
Okay, so we have another question from Salim. So this is a long one. Bear with me here. So with your experience in working in designing competition aircraft, so the aircrafts you're talking about built for competitions, what do you think drives the technology forward more? A strict adherence to the constraints of the competition, or perhaps engineers bending some of the rules with their own interpretations? We have seen several instances of the guys in F1, the Formula One and MotoGP, come up with indigenous solutions, mundane problems through subtle bending of rules, and ending up getting banned, and as a result of technologies never being pursued later. Would love to know if you encountered any such issues in the field. And I think there's a connected question to that so it's the two questions have been merged already. Okay, so I think Salim is trying to touch on the topic of whether it's more progressive to basically comply with the rules of the competition, or sometimes sort of bend the rules to win, I guess, for an advantage, and that just drives the technology in some way.
Yeah, right. Again, really good question on that specific. So in designing the rules, and I've been involved in some of these meetings to figure out how to approach it, and this is one of the questions. You want to have enough flexibility that people can innovate. One of the real endeavours of this competition in AeSN is to foster the innovation. But you do need to have a framework, and you need to have some limits. And so coming up with, for example, should it be, if you want to get an easy race format going, maybe you could just have a standard battery pack or a standard motor that everyone has to use, similar to what the original AeSN Formula One air racing was. It had a standard engine, and you could just tinker a little bit with certain properties of it. But at the moment, AeSN, they definitely want to have the broadest input of technologies to the race, and have the minimum rule set. So having a power limit, I think that's fundamental, because you've got to constrain the design somehow, and the power limit is a very effective way to constrain the design overall. You don't want people to go too far in one way or another in the safety. So having a certain size of aircraft, a certain wing area limit, that you can't reduce the wing area so far that it becomes problematic for handling. You've got to have some basic rules. and then you've got to try to see what's available to, that people are going to be able to access in the commercial market, what they might be able to come up with themselves, and then try to balance that so that you do get people involved. And we have to remember also that the people who are in the racing environment at the moment are super experts at what they do in terms of the airframe construction, design, the engine construction, design, integration, but have very, very little familiarity with electric systems. So one of the agendas is to be able to improve the people out in the field, improve their experience and their skills in electric systems. And so it's probably, I think at the moment, a good mix to enable just the bare minimum of rules. Where there has to be any standardization or limits, just implement those, and then see what people can come up with, how they're going to design their machines, where the problems are, and get feedback off that. The first race should occur within a year, sometime during later next year. It's been delayed again for obvious reasons, but as this process shakes down and people enter the competition, they become on the list of competitors, they communicate with each other, they start to find out what's available in the market, they look at examples such as we're doing. We're very open, so we're not going to be a competitor. We want to do something which can enable everyone to look at it, understand what's good, what's not so good, what can be done better, what can be optimized. And that way, I think you'll find the real innovators come through, and then everyone benefits out of that.
Okay, thank you. We have another question from Jivan. I think Jivan is trying to touch on the topic of if the aircraft is fully electric and you're flying high altitude, for the electric propulsion system, since you require, you're running cabin pressurization and all the HVAC for the cabin, would an electric power propulsion, primarily an electric propulsion system, struggle in a scenario, for example, that we are in right now with Corona and everything, where you need to, continuously filter out the air? So broadly, I think what the question is, would electric propulsion system primarily be able for a larger aircraft to supply not just the propulsion for flight, but also, take care of the internal electrical demand?
Yeah, well, that is one of the problems that's been faced and worked through in research and development. There's a few things that you've got to handle all the systems. One of the other major ones is de-icing, so having all weather capability and having enough of the right kind of de-icing that's relatively low energy requirements. All of the other systems that need to be, the control system, servo motors for the flight controls, environmental conditioning system is obviously a clear one, but on that one, there is now a precedent, at least, of a couple of commercial airliners not using engine bleed air for pressurization. They're using electric systems for that. In terms of COVID, there's an opportunity there, I guess, and maybe a cost, but one of the good things about using engine bleed air is that it's been through a very high temperature cycle and is really purified by the time, presumably as long as there's no leakage in the engine, but by the time it gets into the cabin. I think the same can be true of the electric-driven air cycle machines. It's another load, it's a big load, and it's another problem for the energy storage. There are other means of, let's say, decontaminating and cleaning the air in terms of filtration. I think one of the very interesting ones at the moment is in terms of UV scrubbing, so having a UV decontamination process on the cabin air. But in general, the environmental conditioning systems and the other aircraft systems are really significant loads, as well as the propulsion system. So it's another thing that has to be very carefully looked at when you're doing the overall system design.
Okay, another question is from Aslam Mikrani. I'm about to do masters in aircraft design. I would like to ask Richard, what are the different aspects of the aircraft design which will have more impact in the aviation industry in the future? So I guess broadly looking in the future, where do you see the scope will be?
Yes, there's a lot to that. We've been talking a lot about energy and emissions, which is very significant at the moment. Allied to that, there's airspace management. So the current systems that are used in heavily trafficked areas in commercial air transport are very old systems that have been continually adapted and upgraded, but they're very suboptimal. So there are huge areas to improve air traffic management systems to help optimize the energy efficiency, but also just the traffic efficiency in a network. Now, aircraft design can help address that in itself, in terms of you can have aircraft that are better able to take off and land from smaller aerodromes, better at certain types of mission performance. But the actual, the area of automation, both for air traffic management, but just for pure automation of aircraft, we're starting to see this come in more. There's a lot of UTM concepts in air taxi, eVTOL. It's wrapped up in the same problem, trying to optimize and get the air traffic management system working much better and much more rationally than it is at the moment. There's stuff in automatic control. So recently there's been a few certified examples come out in the last couple of months of an automatic landing system for Part 23 type airplanes, where it's a fully autonomous landing system in an emergency. That's only going to keep rolling on to get better and better until basically you've got much more autonomy in aircraft level and more autonomy in airspace management level. So that's got a lot of potential, not to be underestimated by any means.
Thanks. Okay, so another question is from, Richard, we are closing towards the end, but if you don't mind, we have a couple of more questions.
Yeah, sure, go ahead.
So a question from Asis Mananda. Amazing concept of using the motorcycle pod as range extender. How many pods do you think you're willing to accommodate in an aircraft? So how many pods will there be? Like, for a large aircraft, will there be pods for everyone? How will it work?
Well, the baseline is one, but yeah, so fundamentally though, you can go larger, you can have more. So, you've got to balance the size of the aircraft. If you have, say, a two-seat aircraft, which is one of the examples that I've given, carrying that range extender may convert it to a one-seat aircraft. You might not have the payload capacity. Actually, that's already a problem that's standard on small airplanes at the moment. If you put full fuel, then you might not be able to carry all the passengers and baggage. Now, if you've got a four-seat aircraft, it may be a pure electric four-seater, and you've got a two-seat scooter that has enough, or maybe doesn't have enough power for that four-seat aircraft, then clearly adding another scooter and having maybe one or two people on board the aircraft is an option. And then really there's no fundamental limit. You start to run into some logistics problems and maybe aerodynamic issues as if you want to start adding more and more external, effectively they're external payloads. But yeah, I can certainly see having two on board. That's not out of the question, and depending on the size of the aircraft. But then at some point you have to wonder, do you have more of the small one or just a couple of bigger ones, and where's the cutoff and the payoff of that? So that's a different question. It's a different technical area in trying to do that optimization.
Okay, so we have 3 remaining questions. I think 2 questions from Biraj and Prabhat can be combined into a question that is related also to a question that I had. So a question from Biraj was, I think he was referring to the NASA X-57 Maxwell aircraft with multiple propellers. So is there a distinct advantage between having multiple propellers like in that aircraft, or instead of having like a single large electric motor? And a similar question, sort of connected question from Prabhat was, is there a problem charging the batteries for an electric propulsion system? Which I think is a pretty obvious question one can think of when you think of integrating a propulsion system like that. And I think a question I had connected to that is, So how do you see the efficiency of a electric motor connected to a gas turbine power plant, for example? Like, do you see it significantly improved? Is there a range during the flight where you would prefer to use, for example, for a hybrid car where you can have different speeds to pick for, when you want to use what propulsion system? Is there that kind of a range that we can divide to make that aircraft more efficient?
Yeah, okay. Again, really, really good questions. So on the Maxwell project, having multiple propellers on the wing, there's a couple of ideas behind that. One of the main ones is reducing the wing area. So having effectively a blown wing, you can get a higher coefficient of lift with a much smaller wing, and therefore less drag for cruise. So you can do your takeoff and your landing by blowing that wing with all of the thrust available from all of those propellers laid out along that, typically the leading edge on that in that case. And then in cruise flight, you can fold or feather most of those propellers and just run some, I think in that case it's tip propellers, and the tip propellers are also potentially advantageous in terms of restricting the tip vortex or recovering some energy out of that. So it's still up in the air a little bit, so to speak, as to the overall advantages of that. There's a lot more losses in having all those propellers running. You've got all of those individual tips from those relatively higher disk loading, smaller propellers operating, but it's not operating all the time. So for takeoff and landing, or takeoff and go around or whatever, you're not suffering those losses, but you sort of carry all that mass around with you all the time. And is that a big trade against having high lift devices on the wing or a larger wing? It seems like for certain types of aircraft and certain missions, the trade looks good. I mean, you can look up any number of papers on that and see where and how it works. But the thing is, it's worth exploring, and it's something that really wasn't feasible until electric motor design and associated systems became feasible enough, because you simply couldn't add all of those propellers onto the wing and have them mechanically driven, for example. It's a nightmare to mechanically drive any number of those props, whereas with electric, it's really easy. So you can look up papers on that about the trade-offs for having that spread out wing blowing and also instantly increased disk area, disk loading, scenario where you've got trades there. The next part was about battery charging. Yes, very, very critical issue. A limiting factor in terms of cycle life of batteries. If some aircraft are going to be viable to be pure electric, the battery cost is a big one, big component of the overall system. You've got to make sure those batteries have a long cycle life. Charging and discharging rates, temperatures, controlling those is a very, very big part of that equation for cycle life. You want to have, say, 2,000 cycles for the battery, and you can do it if you're very careful about your charging and discharging and very careful about the temperature profile on those. Then, of course, there's infrastructure. A small aircraft battery recharging on a local airfield is not a huge load. Trying to charge a very big battery or a whole lot of aircraft at one time on an airport, that's a huge load. So you've got to look at where you're getting the energy, the electricity, how you're distributing it, how you're storing it, in buffer potentially. These things are being kind of unrolled in automotive landscape at the moment, so it's not a showstopper, but it's a big issue. And then the final one about efficiency of gas turbine, electric hybrids. So the thing is, to some extent, you do get advantages in a similar way that you get on a car. So you can downscale the engine, having it running at a particular load point, which is the max efficiency point, and not needing to run that engine off design points. So you've got a smaller engine and you're running it more efficiently. Even with an aircraft that it's not as notable, because you might be cruising at 70% of your maximum continuous power, whereas in a car you might be cruising at 15 or 20%. But it's still significant. And then there's, depending on the role and the mission of the aircraft, there's other advantages. So being able to take off using a huge excess thrust, big boost thrust, which electric motors are very good for. You can pump a lot of energy through them, maybe constrained for time as the thermal profile dictates, but getting off the ground an initial climb, that's the difference between having a viable mission and non-viable mission. So it is about being able to adjust the load cycle to optimize each individual component, but it's also about how a hybrid combination can optimize the performance of the aircraft or vary the extremes of the performance of the aircraft.
Okay, thank you. So we have one last question from Hari. So it's several questions all connected and merged into a single one. Which electric motor, when you're talking about selecting electric motors, Safran and others, have you selected for your project at Nottingham? And what is the price range for such motors? Also, which company provides the most economic in terms of price? Which company provides the most economic electric motor? And also, could you recommend some resource materials, books, handbooks, website to those who wish to design electric aircrafts? Could you recommend some interesting competitions in design of electric UAV for students? So I think, so it also sort of leads Richard to this, thing that in Nepal, we are heavily focused on development of UAVs, particularly in our institute. And I think, all of these things about electric propulsion system actually leads significantly to the motivation we have as well. And so, yeah, could you, give your insights on that?
Okay, I'll see how I go. In terms of electric motor selection, and so really it's going to depend a lot on what type of aircraft you're proposing the motor for. Is it going to be a certified aircraft, sports, recreational, potentially transport? So you've got to look into how that's going to be certified potentially, or the reliability versus the cost. There is a lot of, there's a huge range of electric motors in terms of size, scale, quality, efficiency. So first of all, look at the application, and that's in terms of power and size, but in terms also is it, what's the certification category, if any, to where you should start to look. There are many that are going to work. And then some that are going to be easier than downstream to actually get your aircraft in the air and operational. We chose the YASA initially mainly because it's a local company, and we've already got some links with them. It's a UK company. We're using UK funding for this project, and we're trying to obviously promote UK industry. These motors here, the MRX, they're also a bigger range, so they've got a lot of different power and size ranges. I'm not pulling these ones out only. There's really a lot, and you really have to just Google around a bit to find out where they all are, and have a look in general where they sit in terms of the quality and the efficiency and the certification ability of them later. For an example, if I look at the Safran unit here, they've got a larger one now, I believe. This particular one, I think, was a 45 kilowatt, whereas this YASA here is 100 to 150. So we're not really directly comparing the same size, but if we compare the cost, I think this one is around about, let's say £15,000, maybe 10. Somewhere in that range. It depends on what other bits and pieces you get with it. Whereas I think the Safran, last time I heard, it was like 40. So now this is automotive grade, this is aerospace grade. I think we could say the same about the Rolls-Royce Siemens type motors. So and then I think the MRX are something like below that, maybe 5 to 8. And there's pros and cons everywhere, as with all these things, but it really depends on what, first of all, what your airplane's going to do, where you want it to go, how you want to develop it. And then I think the last thing is about design literature and electric aircraft literature. Well, I haven't got any off the top of my head, but they are out there. There are textbooks that I know about and have seen in this field, specifically on this electric aircraft, both the broad system design and also the propulsion design and other subsystem designs. I think they're easy to find. I could probably look some up later. I would recommend just having a look in, again, a Google search. You'll probably find from some of the conventional text publishing houses, there are titles available. Sorry that I just don't have any in my mind right now. Oh, and also, of course, there's any number of research papers. So papers are being published all the time. Even in the last 5 years, you'll find hundreds, literally hundreds of research papers that you can download or obtain somehow.
Okay, thanks. So I think that's all for the questions. And Richard, if you don't mind, at the end, let's look at the presenter, because I think a lot of the attendees have not been able to see the presenter in a full view.
Sure.
If you can exit the... Okay, so, like as I was mentioning before we started, I think Nepal does offer a pretty good testing ground for these kinds of vehicles, I think. So, if you wanted to test some of your aircrafts in the future in Nepal, you are, please be our guest. And I think like our interest has particularly been for a while in development of UAVs. So I think we will jump into, electric propulsion even more. And that's where I think the question from my colleague Hari was coming from. And we, at least from our side, will be keenly looking at the developments on your end, and seeing like how that can impact the kind of aviation industry as well as general aerospace we'll have in Nepal. So with that, I'll hand it over to the president of Aeronautical Society of Nepal, Mr. Ashish Manandar, to close the session. And Richard, if you had any closing remarks, please do.
All right, thank you.
Thank you, Mr. Richard, for your insightful webinar. Yeah, I was really impressed by the design of the pod. Yeah.
I think we all loved that idea.
Yeah, that's really fascinating. Yeah.
Yeah.
It's been very popular, that one. When I came up with it, people thought it was a bit crazy, but as we developed the looks and the feel of it, the pictures of it, people understood it. It's still quite a popular one in media.
Yeah. Thank you very much. Yeah, and thank you all the attendees for attending the webinar. I hope you guys knew more about the electric propulsion in the aircraft, and not only the vehicles, right? Since the EVs are popular these days. So yeah, and I hope you guys had I think very good understanding of the electric propulsion. Yeah, I'll hand over to Sudip. Thanks for being a wonderful moderator. Yeah, and thank you everyone for attending. Yeah, Sudip.
Yeah, from my side, thank you, Richard, and also thank you, Dimitri, for getting us connected. Yeah, so over to you, Richard, and then we close the session.
Yeah.
Okay, so if I get to close it out, well, thank you all for attending, and thank you, Ashish, for those words, and Sudip for moderating and setting everything up. And I'm sure we'll get a presentation from Dimitri sometime in the future,
yeah.
even though he's been absent now. But that's been my pleasure. So thank you very much, and I'm sure happy to be in touch as well.
Thank you.
Mm.
Thank you, everyone.
Thank you, everyone. Yeah, thank you.
Thank you.
Bye.